In our first induction problem, we're going to prove the Gauss summation formula. And the Gauss summation formula says that when you add up the first n natural numbers, you get n times n plus 1 over 2, and then this is of course for, let's quantify this. This is for n bigger than or equal to 1. Now, we're going to give two proofs of this with induction. We're going to give an algebraic proof, and we're going to give a sort of a visual proof or a graph theoretic proof. And our algebraic proof is how we're going to start it off. It's going to be a little bit more algebraically intense than our previous examples, but not too bad. So whenever you're encountering a question about all natural numbers, this is saying for every natural number, this formula holds. The first thing that you should think about is to use induction. Okay, so induction is applied almost as a knee-jerk reaction whenever you encounter a statement about all natural numbers. And before we even get started with induction, we should convince ourselves that this formula actually works for some values. Before we try to prove it works all the time, we should probably convince ourselves it works sometimes. And what I like to say is we need to sort of settle into the problem. Make it a cup of coffee or something. So what that means in terms of this problem is let's plug in small values for n and just verify that it's true. So if n is equal to 1, what does our statement about natural numbers say? In fact, let's be a little bit more, let's have some more notation. We have this statement p of n. For each n, we have this statement. And let's write out what p of 1 says. So p of 1 is going to tell us 1 plus add up to 1, but we're already at 1, so we stop, is equal to 1 times 1 plus 1 over 2, when n is equal to 1. The formula on the right-hand side looks like that. Now, this is a question that we have to then compute both sides of to see is it true. Now, on the left-hand side, there's no computing 1, 1's just 1. On the right-hand side, we have 1 times 2 over 2. 1 times 2 over 2 is, of course, equal to 1. So we're golden. I guess I'll do a golden check because we're golden. All right, so it seems to work when n is equal to 1. Let's try out 2 now. All right, so with 2, we have to start off at 1, and we have to stop adding when we get to 2. So 1 plus 2 is where we stop. And on the right-hand side, n is 2. So it's 2 times 2 plus 1 over 2. And let's see, I think the 2's are going to cancel for us. And we're going to get, it looks like 1 plus 2 is 2 plus 1. Let me scroll down a little bit here. So 1 plus 2 is 3, 2 plus 1 is 3, so it looks like we're golden again. Great. All right, now at this point, we would, try to prove it. Let's do one more step. Let's do on the right over here, let's do p of 3. Let's scroll back up so we can look at the formula. And what we need to do is we need to start adding at 1 and stop adding at 3. And then we need to plug in on the right-hand side, n is equal to 3. So let's see, on the left, we get 1 plus 2 plus 3 is 6. And on the right, we get 3 times 4 over 2, which is 12 over 2, which is 6. Okay, so we're golden here too. So it seems to work at least for the first 3 cases. And so at this point, we would try to now prove it, and we want to prove it with induction. So let's do that now. So we'll be really formal about this. And it's always good to tell whoever is reading what you're, the proof, which is either me or, one of your colleagues, or whoever is, what you're doing. So we'll start off by saying, of course, in math, we always say we, because we do things together. I do nothing alone. We apply, and we can say we apply the principle of mathematical induction, but since this is a presentation, I'm just going to say we apply induction. The base case is where we start, and that's the first instance. And for us, that's n equals 1. And for the base case, what we have is 1 times 1 plus 1 over 2. And that was the P of 1 that we did already. And we know that this is true. We then proceed to the inductive step. So for the inductive step, we need to show that if one of the steps is true, then the next step is true. So that is, if P of n is true, then P of n plus 1 is true. So for the inductive step, suppose P of n is true. And let's clarify what we mean when we say P of n is true. So that is 1 plus 2 plus 3 plus n minus 1 plus n is n times n plus 1 over 2. So that's what we're supposing is true. And now we're going to tell the reader what we want to show. So we show then that P of n plus 1 is true. What's P of n plus 1? Well, you do something similar, but you add up to n plus 1 instead. And on the right, instead of having an n, you have an n plus 1. Okay. So here is our assumption, or hypothesis, if you like. And here's our conclusion. And we want to go from the hypothesis to the conclusion. Let me scroll down a little bit. Let's start maybe by just doing some algebra on the right-hand side. It's looking a little bit messy. N plus 1 is, of course, n plus 2. So that's what we're going to hope to achieve. So again, we want to start with the hypothesis and somehow arrive at the conclusion. So how can we do that? Well, the way in which you go from the hypothesis to a conclusion, at least if you compare the left-hand sides, is you need to add on an n plus 1. So if we take our hypothesis line and we add on an n plus 1, we get to the conclusion left-hand side. So let's do that. Okay, so I'm going to scroll down a little bit more. So since 1 plus 2 plus 3 plus n minus 1 plus n is n times n plus 1 over 2, that's our hypothesis. We can add n plus 1 to both sides to get, right, I'm going to scroll down quite a bit now, to get 1 plus 2 plus 3 all the way up to now n plus 1 on the left, but we're also adding that on the right. And this is good, maybe in a bubble over here. Now we know that the left-hand side is right. And now we just want to do some algebra on the right-hand side. So how do you do algebra here? Well, you find a common denominator, right? And that's going to be a 2. And then you have a common denominator, so you can now add guys. And then both of the terms in our numerator have an n plus 1, so we can factor it out to the left or right, but I'm going to choose to do it to the left. And that's what we get when we factor out. We have an n from the first term and a 2 from the second. And let's just see, on the left-hand side of this, we have the left-hand side of P of n plus 1. And on the right-hand side, we have actually the right-hand side of P of n plus 1. That's what we had earlier. So we conclude P of n plus 1 is true. That's what the inductive step tells us. And then we need to write a concluding step. So, or a concluding sentence. Thus, I'm just going to describe what the formula is, although you could put the formula here if you like. Thus, the Gauss summation formula is true for all n bigger than or equal to 1. So we did the base step and the inductive step, and then from that we can conclude that it's always true for any finite n.